Okay, good morning, everybody. I see that students are connecting slowly, and therefore I think that Alessandro can start slowly this second lecture. Exercise is related to the course of Professor Maiani on multiquark states. And so, Alessandro, please.
Okay, I will start slowly then.
Yeah.
So, well, I have only 1 hour today, so I want to discuss you just a couple of topics and exercises. One of them is related to the heavy quark diquark symmetry. And the other is a brief introduction to scattering amplitudes that is related to the lecture that Professor Maiani will give later today. Okay, so let's start on the first thing. What's this heavy quark diquark symmetry? Well, as we mentioned several times, the heavier is a quark, basically the less it interacts with the less, oh, I forgot another. The less it interacts with the other quarks in the hadron. Okay, so that means that if we imagine to have a D Meson, for example, or a B, even better for a B Meson. So let's put a light quark here and a B bar here. So this would be a B0 hadron, a B0 Meson. The effect of the B quark here, of the heavy quark, is basically just to provide a color source, but it doesn't really interact with the rest. So the effect, for example, of its spin is suppressed by the heavy quark mass. I mean, we saw that the common magnetic couplings are proportional to the inverse of the quark mass. Okay, so the heavier the quark, the less it interacts. Then you can say, okay, what if we have a similar thing where we plug 2 B quarks? Okay, something like this. So this guy would be a cascade double B minus. And what's the idea? Well, color-wise, this guy belongs to the 3-bar representation, and this guy, we know that a diquark is in the anti-triplet as well, because we are inside a baryon, and even if you consider this as a separate object, you know that the 3-bar is attractive. So diquarks tend to belong to the 3-bar representation. So color-wise, they look similar, and we know that the interaction of spin is also suppressed. So you expect to have some symmetry that relates these two guys, okay? And we can make, as an exercise, we can understand what are the violation of this, so the splittings, if we assume that there is some small difference related to this, and see what kind of relation we can get. And in particular, we want to calculate the mass splitting of the Meson sector here for charm. Okay, so the mass of the D star, which is the vector Meson, minus the mass of the ground state pseudoscalar D Meson, compared to the equivalent if you replace the charm quark with 2 charm quarks. Okay, so this would be the so-called cascade double C, and you can compare the spin 3/2 with the spin 1/2, the ground state. Okay. Well, we learned about the mass formula, okay, and the spin-spin interaction. So we can immediately write, for example, what is the mass of the D, star or not. And what's this? Well, the content in quark is mass of the charm plus mass of the light quark. We assume isospin symmetry. Okay, so whatever light quark is fine. And then we have what? We have the interaction between the light quark and the charm quark times the scalar product of the spins. Okay. Let me stress that these two quarks, well, the quark and anti-quark belong to the singlet representation. Okay, we know that the Meson must be colored singlet. So, with this 100 times, this would be the same as this. This would be the spin of the D Meson squared minus the spin of the charge squared minus the spin of the light quark squared. Okay, so this is 3/4, this is 3/4, and this is it could be 2 for the case of the D star, which is a vector, or 0 for the case of the pseudoscalar. That means that this mass difference, I mean, all these terms are the same, so the only difference that you get is this times the spin squared of the D star, which is 2, and the spin squared of the pseudoscalar, which is 0. Okay, so you get twice KQC. Okay, is that clear? What happens for the cascade? So cascade is, so let's write it this way. Good. So we have 2 charm quarks and 1 light quark. So these are the masses first. And then we can have all the possible interaction between the quarks. So you have twice KQC, spin of the light quark times either the first charm quark or the second charm quark. Or you can have the interaction between the 2 charm quarks. Okay, these are just the same of the mass formula we wrote on Tuesday. Okay. Let me add a couple of things. So now, instead of the singlet, in the case of Meson, the 2 quarks belong to the 3-bar representation. So let me put a 3-bar here, and similarly a 3-bar here. And the other assumption that we make is that we know that KCC, since these chromomagnetic couplings, as I said, depend on the inverse of the quark mass, are suppressed with respect to the light quark run by a factor of MQ over MC. Okay, so the heavier the quarks, the heavier the heavy quark, the more suppressed this KCC is. So we are going to neglect this term here. Okay, and we just have this first guy. Now we can write here, so 2MC plus MQ plus KQC, 3-bar. And here we have what? The total spin of the cascade, possibly star, squared, minus the squared of the light quark spin, minus the spin of the CC diquark squared. Okay. Well, these are not really relevant, but let's write this anyway. This is 3/4, and the 2 diquarks are identical. The 2 quarks are identical, so they must be in spin 1. So this will be 2. Nevertheless, this doesn't matter because we want to just calculate the splitting. So this delta M CC star is what? All these numbers are the same. The only different thing is the spin. So we're going to get, as in the previous case, KQC, now 3-bar, times the difference of spin. So the cascade star is a spin 3/2. So here you are going to get 15/4 minus the standard, the ground state cascade CC is spin 1/2. So you're going to get another 3/4 here. Okay, so this difference is 3 KQC in the 3 bar. Okay. So you see it's almost the same as this splitting here. Okay, not exactly the same, because here you have the singlet and here you have the 3 bar. Okay, but what we calculate on Tuesday is that another contribution to these chromomagnetic couplings is the relation of the Casimir. Okay, so you can say that this is proportional to this Q factor that depends on the representation this guy belongs, and this QR is related to the Casimir, so it's 1/2 of the Casimir of the representation minus the couplings of the Casimir of the representation of the constituents. Okay, and we saw that for the singlet this is minus 4/3, and for the anti-triplet this was 1/2 of that. Okay, so if you like, the strength of attraction in a diquark is 1/2 of the strength of attraction in a meson. So if we consider this factor of 1/2, we can claim that the KQC in the 3 bar must be 1/2 of KQC in the singlet case. Okay, so this allows us to relate this mass splitting here in the baryon sector with a mass splitting in the meson sector. And the relation that you get, and that you can find in the literature, is that the splitting in this baryon sector is 3/4 of the splitting in the meson sector. Okay, is that clear? Any question? Sorry, just 1 second, sorry.
Okay, in the meantime, you can think if you have any questions to Alessandro.
I'm back, sorry. Okay, so we conclude this part about the quark interaction. So let's go to the amplitude part. Okay, and well, let's say for a second why we want to do that. So we're interested in particular in the case of the X872, that we know that there are explanations of this in terms of the zero star bar molecule, at least the combination of this with positive charge conjugation, but I'll drop this subscript in the following. What does this mean? Well, it means that if you were able to scatter at the 0 meson and at the 0 star bar meson, you will be able to see something that is related to the X372, because if this is a bound state of the two, there will be a prominent signal in this. Well, of course, you cannot do this because the D0 is not a stable particle. You cannot produce a beam of D0, and it's even more complicated for the D0 star. But what you can claim is, first of all, that the D0 is stable under strong interaction. Okay. The lifetime is order of, well, I don't remember exactly, let's say picoseconds. So it's a very long life in terms of strong interaction. The D0 star, it's actually not, okay, so we shouldn't do this, but nevertheless, its width, it's very small. It's order of, well, there is no real measurement for the D0 star, but still there are estimates that tells us that this is of order of 65 keV. And if we compare with the width of order of MEVs that we are interested in, this is still very small. So there is a reasonable limit when you can neglect the fact that these states are actually unstable, and then you can discuss about the possible scattering of these two mesons. The other thing that you are going to neglect at first order in order to consider this is the fact that this scattering amplitude here can couple to other possible mesons. We know, for example, that the X decays to jet psi and 2 or 3 pions. Okay, so there are inelasticities. Okay, that means that the scattering of DD star is not purely elastic. If you start from DD star, you may end up in something else. But since there are indications that the width of the X is mostly saturated by this DD star, these inelasticities are actually small, and you can neglect them at first order. Okay, so that means that in order to discuss what I'm saying in a second, we are going to restrict to elastic scattering of stable D0 D star bar mesons. Okay, which is an approximation, but a well-founded approximation. Then there are ways of, let's say, get down from this approximation. Okay. Any questions so far? Okay, so let's keep talking about this. So we have to introduce, well, I assume you know what a scattering amplitude is. If you think non-relativistically, for example, we can put a target of the D0 star bar here at rest. We imagine that we can make a beam of this D0 that propagates as a plane wave, gets here on this target, and then it gets scattered all over the place. And the wave function that you're going to get for this D0 is your original plane wave that you started with, plus something which is called the scattering amplitude that modulates the outgoing spherical wave. And this depends on the momentum, and in principle depends on the angle, but we are gonna study, we know that the effect of the X is visible in S wave, so that means that we can neglect this angular dependence here and assume that the scattering happens isotropically. Okay, and this is the so-called scattering amplitude. Okay. Among the properties of this scattering amplitude, we have the so-called unitarity. unitarity is related to the fact that the probability is conserved, so that the flux that is seen coming from this plane wave must be the same flux that gets out throughout this this outgoing spherical wave. And in terms of the amplitude, well, you can write this in several ways, but in terms of the amplitude, this puts constraints on the imaginary part of the amplitude. Okay. This basically tells us that the imaginary part of the amplitude above threshold, so for k greater than 0, and I will tell you in a second why I have to specify this. This is proportional to the modulus squared of the scattering amplitude. So first of all, it's positive. And there is also a phase space factor here that depends on the normalization. If we stick to a non-relativistic normalization, it is just a factor of momentum. Okay, because the two-body non-relativistic phase space is just proportional to the momentum. Okay. You can rewrite this relation in this way. That if I calculate the inverse of the amplitude, then I calculate the imaginary part. This is minus 1 over k. Okay, I mean, you get how I can do this. I can just divide by the modulus squared, and this is a real thing that I can put inside the imaginary part. So I get f divided by modulus squared. So this is 1 over f star, and this is the negative of the imaginary part of 1 over f. Okay, so I get this relation. Okay, and this is pretty much one of the little things I know about the scattering amplitude in general. Okay, so all the rest depend on the specific model, on parameterization that can use to describe the interaction, and you can calculate this amplitude if you assume some microscopic model that controls what happens in the interaction between a Dirichlet star. But there are a few things that you can say in general, and basically they all depends on this relation here. Okay, this is unitarity. Okay. So one other thing I can do is to use this information to write a generic form of the scattering amplitude in terms of the so-called K matrix. So what I can say is just to use this information and plug in an ansatz that satisfies it automatically. And this is very easy because I know that the imaginary part, sorry, I miswrote here. This is just K. I know that the inverse of the imaginary, the imaginary part of the inverse of the amplitude must be this factor here. So I can just write something like this. Okay. And whatever I put here is basically all the rest. That is usually called K matrix, or well, matrix for historical reasons. And the only thing that we know is that this is a real function of K. Well, actually, for other reasons, we know also another thing. It's an even function of K. This is related to the analytic properties of the amplitude, but I will not talk about this, and I will just I'll ask you to trust me on this point. Okay, and you can see that whatever I choose, whatever function I choose, this unitarity relation is automatically satisfied. Okay, any question? Okay. So as I said, there are not many things I know from first principles, but what I can study, for example, is approximating this guy. And the idea is, if I want to study only the region with K very close to 0, I'm interested in what's happening at threshold. And in particular, if I assume I have a shallow bound state, that means a bound state that with very small binding energy, so it appears very close to threshold, then I can approximate this unknown function. I know nothing about this, but I can approximate it with a constant. Okay. You can think of, okay, this is in general a complicated function, a complicated even function of K, so I can expand in powers, constant plus constant on K squared times plus, etc., etc. And I just stop at the 0 order term because I'm very, very close to threshold. Okay. And conventionally, this constant is written this way, and A is called the scattering length. So this is also called the scattering length approximation. Okay. Be careful to this sign here, because you can find it different in different books. I mean, this depends on the convention that you choose on the scattering length. Of course, I mean, well, there is a possibility of choosing two different things. There are always two groups of people that follow different choices. So I will stick to this convention, but you can find others in the literature where you just have to flip the signs and understanding what convention you are talking about. Okay, so what are the properties of this guy? First of all, what do bound state have anything to do with this? Okay, so bound states are poles for negative energy. Okay. What's the idea? Well, I mean, you know that states are related to poles in the propagator, right? And this scattering amplitude is also, in some sense, a sort of the propagator, because it knows about the propagation on the intermediate states in the scattering. So the existence of other states must be signaled by the fact that there are poles. And for negative energy, because you know the bound state have a binding energy, so if you start from physical scattering, so you have positive energy and you trust energy conservation, they cannot just fall in a bound state. Okay, they must scatter, but there is something going on here by the fact that they really would like to fall into this bound state, but since there is energy conservation, they cannot just stick and stay together. Okay, so they will just move apart, but the cross-section will be enhanced by the existence of this bound state, and this is related to this pole that appear in the scattering amplitude. Okay, so there are consequences of using this scattering length approximation related by the fact that this amplitude now depends on a single parameter, okay, just on the scattering length. And this relation has been, as far as I know, has been first put forward by Landau, or at least, let's say, formalized by Landau. And it's a relation that happens between the binding energies of these bound states and the coupling to the constituents, so to how strong these bound states couples to the channel we are considering. That is a relation between the pole position and the residue. The residue is related to the coupling of the bound state to the constituents. Okay. And this is kind of obvious from this functional form because you have a single parameters, but you have two quantities. Okay, so there must be a relation between the two. Okay. So let's calculate this relation. First of all, I told you that these are poles for negative energy, but here I wrote a momentum. So of course, I have to remember that the relation between energy and momentum is as simple as this. Mu is the reduced mass of the two constituents. Okay. So and I can obtain the energy if I just multiply by the conjugate. So let me factor the minus sign. So I put plus and an overall minus sign here. Just have less signs floating around. So I have this and this. And this becomes 1 over a squared plus k squared. And let me rewrite k squared as 2 mu energy. Okay, so if I factor this 2 mu here, I have minus divide this. Okay, and I can immediately see that the pole here, the position of the pole, which is, well, conventionally we consider, I mean, if there is a bound state, we call it binding energy a positive number. So the position of the pole that is for negative energy, we must put a minus sign. So the position of the pole you can read immediately from here is minus 1 over 2 mu a squared. Okay. So now we just have to calculate the residue. And this is easy. You just have to say that, okay, if this is the energy of the pole, the momentum of the pole will be twice mu, the square root of twice mu, and the position of the pole. Okay. So this makes a positive I for the convention of the square root. And this is just 1 over a. Remember that a is positive. Yeah. Or, yeah, a must be positive. And you can see that it must be positive from here, because if you want to go to negative energies, that would correspond to go to imaginary momentum. For imaginary momenta with positive imaginary part. So you need this minus I to be compensated by the positive imaginary part of K, so that minus I times I becomes positive. And then you have a pole if the scattering length is positive as well, because of this minus sign here. Okay, so that means that this sign here is right. Okay, and in the numerator here, I can rewrite everything this way. This is the position of the pole minus the position of the pole plus A, and the residue is forgot an A here. The position of the pole is then just this. Okay, I'm getting twice basically the. I get something that is related to this factor here. I get that the residue that I can call G squared. I'm calling it coupling squared because I have in mind some diagram of this type. So I have the propagation of an intermediate x3 at 72 from a scattering of DD star and DD star here. So it's customary to consider the residue as the product of two couplings. So I'm writing the coupling squared here. And what I'm getting then is that this G squared is twice 1 over 2 mu A, so it's just 1 over mu A. Okay. And if I use these relations above here, I'm getting that this is twice the binding energy over mu. Okay. So I have a close relation between the coupling, so the strength of the coupling of the bound state to the constituents, and its binding energy. Okay. And let me also tell you that there is a normalization here that also depends on the conventions we use. So you can have other factor of masses and factor of pi's and whatever. But the punchline is that you have a relation between the binding energy and the coupling. Okay. Any questions on this point? No questions today. That's bad. Okay. So this is not the end of the story, of course, because we did a bunch of approximation here. For example, we stopped at the scattering length level. So this will be, let's say, this assumption will be loosened later in the lecture today. But for now, we'll stick to this. And let's just see the consequences of what, for example, what happens if A is not a positive number. Okay. Well, this construction doesn't hold, does not hold. I mean, we don't have a bound state if we flip the sign of A, for the reason I basically just told you before, that you need to have a momentum with a positive imaginary part here, so it doesn't match the sign of the first part. Okay, so there is no pole anymore. Well, that's not entirely true. Let me rewrite it again. And let's assume now that A is negative. And this brings us to the concept of virtual states. Okay. You see that, strictly speaking, I don't have poles for negative energies, because if the energy is negative, then I have something like, let's say, a momentum with positive imaginary part. Okay. So now -1/A is positive because A is more than 0, so I don't have poles. But what happens if I consider the other case? Okay, so if I consider K with imaginary part, well, technically you can say, well, the energy is just the momentum squared. Okay, so this will be satisfied as well. The problem is that you are no longer in the correct sheet of the square root. Okay, so square root brings conventions, so you always pick the solution with plus I, basically. But you can wonder what happens if you go to the so-called second Riemann sheet of the square root. And in this case, you still have a pole, and you can see that you can still calculate things. But this pole doesn't relate to the existence of bound states. Okay, still a pole, no bound states. Okay. But what's the effect of this? Well, when you consider the cross-section, you know that the cross-section of the scattering process is proportional to the modulus of the amplitude squared times factor. This is an S-wave scattering, so we don't have to consider the angular dependence. And you can see what's the behavior of the cross-section as a function of the momentum, or as a function of the energy, which is the same. And you can see that in 0, it must go to 0 because of the phase space. The phase space is basically, well, this is elastic scattering, so that's not actually true. What you can see is that there is an increase of the cross-section going close to threshold, and that would be true regardless of whether this pole corresponds to a bound state or not. Okay. So you can call this enhancement of the cross-section that is not related to a honest-to-God bound state as the existence of a virtual state. And this is something that actually exists in nature, and that's the last thing I'm going to tell you. And this is related. This happens for example, in the case of proton-neutron scattering. Okay, you know that deuteron nuclei do exist, and this is the benchmark basically of this shallow bound state. And but they, you know, for example, that the deuteron is a spin 1 object. But if you are scattering 2 particles spin 1/2, sometimes they will scatter in total spin 1, sometimes they will scatter in total spin 0. And well, by Pauli symmetry, you can see that this would be the same as scattering 2 protons or 2 neutrons. So the neutron, for example, would have spin 0. Problem is, have you ever observed a free dineutron in nature? And the answer is no. There are no, nothing like the deuteron. You can isolate deuteron nuclei, but there are no such a thing as isolated dineutron bound state. Okay, so you know there is no bound state for the neutron here. But if you study the cross section of proton and neutron, or imagine that you can actually scatter them two neutrons, you see a similar behavior, so a similar enhancement of threshold, as if there was some bound state. So how you can explain this? Well, you can explain this by modeling the potential between the two states and calculating the scattering out of this. So you can see that if I plot the potential, okay, now the potential is a function of distance, and I can use the most crude model for this, so just a square well. And well, I mean, you know that you can solve the square well in quantum mechanics. The interesting thing is that in 3 dimensions, there is a minimum depth that you need to have in order to have a bound state. Okay, so you can imagine that for the deuteron case, the depth is deep enough to have this bound state. But then if you go to another spin state, also in this case, we'll have some kind of spin-spin Hamiltonian. So the depth of the well will be slightly less, okay? So it will be kind of here. And it will not be deep enough to give you a bound state. But still, maybe the difference is not that small, so you don't expect to have a huge effect in the scattering amplitude. And indeed, this is the case that you have. You can calculate that the scattering amplitude, if you start from this formula here, close to threshold, is just a squared. Okay, so you can see from the formula of the cross section that you are actually not very sensitive. Well, you are not sensitive at all to the sign of this scattering length. Okay, so this is telling you that you can have a similar effect both for this bound state and for the virtual state. Any questions on this? All right, and if you make the exercise, and then I'm going to conclude. If you make the exercise of calculating the scattering amplitude from the potential well, and you take the limit of k going to 0, you can see that the sign of the scattering length actually flips if you crease this critical well. So the sign of this depends on whether the depth of the well is smaller or greater than the critical value that gives you the depth of the well. Okay, so depending on this, you can actually get different signs for the scattering length and similar effects in the scattering. Okay, so now you say, okay, why we care about this? Well, because in real life we are not in this setup that I discussed. Okay, there are other channels. Okay, and the star is unstable. So practically speaking, what does this mean? That if you consider the total energy, for example, of the DD star system, and this is the DD star threshold. So this is where the physical scattering happens. Okay, since you have other channels that couple to this, for example, jet psi pi pi in the case of the X, you are actually able to probe this region below threshold. So in some sense to study the behavior of the scattering amplitude also below threshold, okay? Even if strictly speaking, that would be a forbidden region in the assumptions we started with, okay? And you can use the information from this region to get some more details about the scattering amplitude, and then discuss the effects that Professor Mariani will tell you later today. Any questions on this? Okay, since people are not very active today.
So Alessandro, I understand that what you are telling is very important for the lecture of today, no? By Professor Mariani. So I would invite the students to ask questions if it is not clear, because it's crucial, no? In a sense, to follow. Indeed, what you said is very clear. It was very, very clear. So probably they have understood. So it could be a good sign if questions are not booked.
I also think that it was pretty clear. In fact, very clear.
Thank you. Can I just, Alessandro, if you go up a little bit, when you have done the small plot as a function of k or as a function of the energy, the previous page, mm-hmm. this one, yes. Can you put some reference, some units, some
sure.
Something to just to get an orientation?
Well, you know, series don't like numbers.
Yeah. You're discussing phenomenology, so
yeah, I'm joking. Just because I don't remember the exact numbers.
No, but I mean just the order of magnitude, no, just to
yes,
so because you're discussing very low energies here. So
yes, so let me think. So I mean, here is energy, so we are close to the proton neutron threshold. Okay, so let's say we're starting from 2 GeV, and let's say this is the same plus 10 MeV.
Okay.
We're discussing the low energy part. We know that, to give some reference and number, the binding energy of the deuteron is 2 MeV. Okay, so this is for deuteron. Okay, so we are considering the scale of few MeV where we can see the effect of this. And the scattering length that you get for deuteron is 5.4 Fermi. For dineutron, I don't remember the exact number. It can be minus 10 or 20. I don't remember. But the punchline is that it's negative and it's large. So since it's large, it means that this number here is small. So it corresponds to a pole that is also very close to threshold, just on the wrong sheet.
And in each of these models of these scattering amplitudes for these processes, it is assumed, it is, how to say, nobody has thought that the interaction can be not central, for example. Everything is central and everything is... orbital angular momentum conserving, and it is nothing like the nuclear interaction, for example.
Well, I mean, protons and neutrons, yeah, they're pretty spherical. But yes, you can have, for the case of, I mean, the Neutron, of course, is very well studied and measured. Okay, you have a zillion of data.
No, but I am asking for this models of the Meson scattering. No, if in some cases it has been assumed that the interaction could be more complicated than just central, like it happens for the proton and neutron in the Neutron, for example. No, you have an important contribution from.
Well, it's all a matter of scales, right? I mean, the problem here is that the binding energy, if I think of the X, okay. So now let's put numbers for the X, because I told you about the Neutron earlier. For the case of the X, the binding energy is, you have only upper limits, but let's say you have reason to believe this is, let's say, 20 to 200 keV. So all the effects of anisotropy or things like that are extremely suppressed, and you're definitely not sensitive to this. So people have thought about that, but just they are not relevant on these scales.
Sure. Just speculations.
Yeah. Just because basically, since you are so close to threshold, the only quantity that matters is really the scattering length. You know, all the effects that you're talking about basically correspond to higher orders in K. So you're not sensitive to those. What you're sensitive to is the presence of a hard core, and this is the content of Mayani's lecture.
Good.
And because hard core gives you terms of order K squared, but with a large coefficient. Okay. But all the rest that are related to the details of the potential, they are just basically suppressed by this, so you're not sensitive to those.
Okay, thank you. Comments, questions by the audience?
I have checked that the scattering length in the case of the spin zero channel for the nucleon scattering is minus 23.5, I think.
I remember it was huge.
Yes, it was much larger, minus 23.55 femtometer.
Yes.
You said between minus 10 and minus 20, so you were not far actually.
Yeah, no, I remember 20. So yeah.
Yes, but Sergio, can I comment on this?
Of course, please.
Neutron scattering cannot be done so far.
I know.
Okay, so all information that we have on these scattering lengths are indirect, and they go. One cannot really say that there is an experimental measure because they go through some kind of modeling. So I would be sort of very careful in giving numbers, in particular because these numbers do not help at all. So while for the deuteron we know exactly, for the neutron, I would leave it as it is. I mean, a bit uncertain and quite large, and that I think would be enough for the students to know.
Yeah, that's it. That's the consensus. I mean, it's negative and large. Then precise numbers.
I don't know whether we would ever know. Nowadays, they are doing experiments, even using indirect information from exotic nuclei decay. Right. But I mean, it's a field on which I would be really careful.
Okay, but you can study neutron proton in the spin zero channel.
Yeah, I mean, neutron proton is not a problem. We all know.
No, I mean, if you assume isospin symmetry.
Well, yes. Isospin is different.
Neutron is difficult experimentally, and as physicists, we have to start with an experimental result, I think. Although I know there are groups who claim, I mean, from time to time you see these papers in which they say, oh, the experimental value is such and such.
No, I mean, the point is that this number is so small, okay, because it's 1 over this large number, that you can wonder of, let's say, what's the relative size of this isospin breaking thing? So what's the difference between the dineutron and the spin 0?
Yes, of course. I mean, there are a lot of fundamental, how to say,
So this matters for
consequences.
matters, because now this correction can be relevant.
Yes, yes.
But let's say it doesn't change the picture, okay?
Yeah.
Okay, thank you, Angela. If there are no other comments, I would thank Alessandro for his clear exercises presentation. Thank you. Please send us your PDF whenever you can.